This video is on resonance. Make sure you are taking notes as you watch this. Resonance is when more than one Lewis structure can be drawn for the molecule. Sometimes it's not as straightforward as there's only one way for it to be drawn. And it has to do with the electrons and many times with the bonds. So quickly about the bonds. Single versus double versus triple. You've probably seen this when you've built them in your model kit, but a single bond is the longest bond, and as you go across, the triple bond would actually be the shortest. So these electrons are actually pulling closer together as you get more of them in there. So double would be in the middle. And in terms of strength of bonds, if it's the longest, it's also the weakest, which makes a triple bond the strongest. And you could think of this too as your single bonds, you could twist your molecules around and kind of bend them, flex them back and forth. But once you make that triple bond, it's really hard to break it apart and bend it. So these electrons, in terms of resonance structures, they're not localized, they're what we call delocalized. So that means they're not in just one spot. So localized means in one spot, delocalized means spread out. So you may have had local anesthesia, possibly when you've gone to the dentist. Local anesthesia is when they numb just one specific part. So you might have had that in just one part of your gum or one side of your mouth. That's when you leave and it feels like you're drooling everywhere, and maybe you are. Delocal anesthesia would be when basically your whole body is numb. So that would be like when they put you to sleep. So these electrons actually are moving around. They're not in just one spot in one bond between two atoms. They're actually spread amongst all of them, amongst the whole molecule. So some examples of this. We'll draw a few. Would be something like ozone. Ozone is O3. And there are actually two resonance structures. So one way you could draw this would be an O double bonded to another O, single bonded to another O. So there are your three O's. You still have to have 8 valence electrons for each of them. So they look like this. So this is one way of doing it. And what we've been talking about so far is the other way of drawing this, you would say, well, that's just looking at it from the other side. Well, yes, it is. So when we draw resonance structures, we do a double arrow between them. But it's basically flipped over. This bond here, this bond gets moved to here, and they switch places. So yes, it's like looking at it from the other side, but when we draw it with the double arrow and we draw two structures, we're saying that these electrons are delocalized. They're actually kind of in both places. They're spread out. So your other resonance structure would be this, with the double bond on this oxygen. So we're not saying it's just flipped around. We're saying it's actually that double bond is on the other oxygen. So these are the two resonance structures for ozone. So we show them with the double arrow between both structures. Many structures have multiple resonance structures. The most famous example is benzene. And benzene is C6H6. And for a while, scientists had a hard time figuring out this structure. With C6H6, they couldn't figure out how this would form with the right number of carbons and hydrogens. And a famous scientist, Kekulé, actually figured out the structure of this in a dream. In his dream, he imagined a snake kind of eating its own tail, so like a circle. So he figured out that this structure was actually circular. So if these carbons are connected in a circle, they have double bonds alternating. So one of the resonance structures would be a carbon, bonded to another carbon like this. So we could have double bond here, single bond to this carbon, double bond to here, single, double, single. Okay, and then it'd have an H off each of these. I'm not going to draw on all the H's. Okay, so each line has an H on it. So there's C6H6. The other resonance structure would have the double bonds in opposite spots. So it's not rotating, it's actually having the double bonds connected to different carbons. So here would be a single bond, then these would be switched. Like so. And then each of these has a hydrogen off of it. So there's a couple other ways to draw this that I want you to be familiar with because you will see these. So sometimes they'll draw, for instance, if you had like C4H, let's see, 6, 7, 8, 9, 10, H10. So if you have butane, right, it's 4 carbons like so. So another way to draw this would be like this. And then each point, so this is a carbon, this is a carbon, this is a carbon, this is a carbon, to simplify it. So when we do benzene, showing this hexagonal shape, you'll see it's drawn many times like this. So each corner is a carbon. And to show that we have double bonds alternating, we do a line here like this. Okay, so there's one resonance structure. The other, maybe your hexagons are better than mine, would look like this. So those are your 2 resonance structures. So benzene, when it's written so much in organic chemistry, they actually wanted to write this shorter and show that both resonance structures were in existence all the time, and they were getting tired of drawing all this. So instead of drawing these 2 that I just drew in green, they'll draw this. So here's your hexagon. And to show that both resonance structures exist, they put a circle in the middle like this. So this, what I just drew in red, is equivalent to drawing both in green and drawing both in blue. Okay, so that is resonance structures.